Hello, BC Calculus students. This is Mr. Johnson, and this is the first section in Chapter 5, which is on areas and distances. And primarily, we're looking at Riemann sums and the trapezoid approximation to evaluate definite integrals. Now, in the notes, you have 6 different FRQs that work through a variety of different problems. What I'm going to do in this video is I'm going to go through 3 of those and highlight some of the main approximation tools that we use. The 3 FRQs that I am not going to go over are all labeled, so they have the year and the number labeled, and you are certainly welcome to practice those problems on your own. Keep in mind that we have all of the keys for those problems in Schoology. You can also work with your teacher on those 3 problems if you'd like, but this video will go over a select 3 of those 6 problems that are in your notes. So here's our first one. It's from 2004. It is Form B, so they used to release both Forms A and B on a regular basis. So this is number 3 from 2004, and it is a calculator allowed problem. So we have this test plane that flies in a straight line with a positive velocity. They give us the units there, and it says that select values of velocity from time 0 to 40 are in the table. So for part A, we're going to use a midpoint Riemann sum with 4 subintervals of equal length and the values from the table to approximate this definite integral. Now remember, with a Riemann sum, you basically have a left Riemann sum, a right Riemann sum, and a midpoint Riemann sum. And all of those are used at different times and for different reasons, really. A midpoint Riemann sum is traditionally quite accurate because of the fact that you're using the midpoint of the interval, and it might be a little bit above and a little bit below the actual value, and so it sort of balances out to a certain extent, depends on the problem, clearly. But your midpoint is never going to be developed by you. At least we've never seen that on the exam. We've always seen the midpoint provided to you. So again, when you dig into this particular problem, we're looking at these 4 subintervals, and that means that we're going to split this up. So we have one interval from 0 to 10, one interval from 10 to 20, and another, and maybe I should re-highlight this. Hold on, let me try this instead. So one interval from 0 to 10, one interval from 0 to 20, one interval from 20 to 30, and then 30 to 40. Now we know this because it says it's 4 subintervals of equal length, and so we could simply take our interval from 0 to 40, we could divide by 4, and we get intervals of 10. What that means is that we have a midpoint provided to us. We, again, are not going to develop a midpoint. And I've never seen the exam ask you to develop a midpoint before. And so we are going to just simply take the midpoint that is provided in the table. We're not going to create our own, okay, or average anything, that type of estimation. So we're going to calculate an approximate for this particular integral. So we have the integral from 0 to 40 of the velocity. Now, traditionally, this integral is depicting the displacement of an object because it is not the absolute value of velocity. However, in this particular case, the velocity is always positive. So this would be the distance calculated here. But either way, we are approximating this because we're using a Riemann sum. And so we're taking the base of this rectangle. Remember, when you let me go up here and draw you just a quick sketch. And this is not for this particular problem, so just bear with me. Let's say you have some data here that looks like this, okay? And this is just in general, okay? I'm not trying to make it specific to this problem. When you're doing a midpoint Riemann sum, and let's say that your graph, I don't know, looks something like this. Maybe we just have a little bit of data here. If you're going to go between, the intervals, let's say that I'm using the data that I have sketched out here. Okay, so we're going to use the midpoint of all of these. So for instance, we're going to use the midpoint value, which is going to be here. And so our first rectangle would be depicted, or the height would be dictated by the midpoint. The next rectangle would have a midpoint here. And so you're looking at, a rectangle that looks about like that. The next rectangle would have a midpoint about there. So your next one would be approximately here. You can see that there's a little bit above and a little bit below of each of these values, but the midpoint is dictating the height of the rectangle. So a left Riemann sum, the left side would dictate the height of the rectangle. A right Riemann sum, the right side would dictate the height of the rectangle, and so on. The base of each of these rectangles, so when we're looking at this this length right here that I'm highlighting, okay, that is going to be the length of the subinterval. So in our case, we have a subinterval that is length 10, but the height is based on the function value at the midpoint of the interval. So if we go back to our problem here, the base is here, it's 10 units, and this would be the height. And the height would be, varying. In this case, all of our bases are exactly the same. Okay, so let's go back to the problem. So we have this integral that we're approximating. We have a base of 10. So I'm writing the equation essentially of a bunch of rectangles. So we have a base of 10, and then we have a height of, the first one is going to be 9.2. Again, I'm gathering that from the midpoint value of that interval. Then we have the next one, which is a base of 10, and then the height there would be simply 7. And then we have the next one, which is a base of 10, and a height of 2.4, and a base of 10, and a height of 4.3. No matter how easy it is to calculate, never calculate this in your head and then write down the value. Always write out your Riemann sum. So always write out the summation of these rectangular areas, okay? Then we know that this, using our calculator, we can just type this in, is equal to 229. All right, now the problem asks us to show the computations. We did that. Using correct units, explain the meaning of the integral in terms of the plane's flight. So we can't just say something generic. We have to talk specifically about this particular scenario and use the correct limits. I'm going to write something down. I'll pause and write it down so that I'm not talking while I'm writing. Okay, so this would just be one example of how you could describe what this integral is giving us. I mentioned that typically an integral like this would be displacement if the velocity was alternating signs, potentially between positive and negative, or maybe it was all negative. In this case, the velocity is positive, and so therefore this would be the total distance in miles that the plane flies. And it also is important, so we've included the units, but it's also really important that you would include the interval of time. So we've seen this over and over again where AP is wanting you to be specific to the problem, not just in the units, not just in the behavior of what's going on in the context of the problem, but also based on the amount of time or at a specific time, or in this case, it's an interval of time for which the situation is occurring. So just keep that in mind that you want to specify when. All right, let's take a look at part B. So with part B, it says that based on the values in the table, what is the smallest number of instances at which the acceleration of the plane could equal 0 on the interval 0 to 40? Now we're looking at acceleration, however, the table is giving us values of velocity. So our initial thought here would be that we're taking a look at the mean value theorem. And one of the reasons for that is that we're looking at intervals. That's all we know. We don't know everything about velocity. We just know a little bits and pieces along the interval 0 to 40. But also we're looking at the relationship between intervals of velocity and the acceleration, which that often that connection is going to be the mean value theorem. So what I'm going to do is I'm going to pause and write out a few things, and then I'll talk through it. Okay, this would be one way to describe the answer to B. We do obviously want to claim the mean value theorem, and we also want to make sure that we are talking about intervals of time, which I mentioned. And by the way, I would maybe add in here, this is probably a good side note because V of t is differentiable on the interval 0 to 40. So maybe include that. That's a really important aspect of the mean value theorem. Otherwise, the mean value theorem doesn't apply. Now, in the problem, it states that. That's why we can claim that. Anyway, so we're looking for when is the acceleration 0. So we're looking at when v prime is equal to 0. So we know, based on the data in the table, that somewhere between 0 and 15, so if we're looking specifically at just this portion of the table, we know that the velocity is the average velocity, is equal to 0, because we could take 7 minus 7 and divide by the interval, and we get 0. And so therefore, we know that by the mean value theorem, the derivative of velocity has to be equal to 0 at least once on that interval, because the instantaneous velocity is equal to the average velocity at least once in our theorem. But then we also know that on the interval from 25 to 30, so right here, we know the same thing is true. We know that the velocity, the average velocity is equal to 0, and so therefore the instantaneous must equal 0 at least once in that interval, again by the mean value theorem. So our conclusion is that there's at least two values for which the acceleration is equal to 0 based on our evidence from the mean value theorem. All right, let's take a look at part C. So part C says that there is a function defined by f of t, and it's used to model the velocity of the plane in between 0 and 40. So there's a function model now that isn't perfectly aligned with the table, but is very close. According to the model, what is the acceleration of the plane at time 30? This is simply a calculated problem. This is something we're not supposed to do by hand. We have a calculator available, but we do have to communicate what we're doing. So you simply need to write down f prime of 30, which is going to be the acceleration, and you don't have to do that derivative by hand. You have to be able to just type it in and communicate notationally what you're calculating. So in your calculator, you'd use Math 8, and Math 8 would give you the numeric derivatives. You would type in your function and evaluate it at 23, and you get negative 0.407694. You only need 3 decimal places, so you could either do 0.407 or 0.408 if you wanted to round. And then our units here would be miles per minute squared, which is our acceleration in this case. And that's it for C. It's pretty straightforward. For B, it says according to the model F, what is the average velocity? We're actually going to talk more about averages later in this particular chapter, but this is something you learned last year. The average velocity is a formula. It's 1 divided by the length of the interval, which in this case is 0 to 40, so it's just 40, of the integral from 0 to 40 of velocity. And again, we'll talk about this a little bit later, but this is the average value of a function in integral form. And in this case, we don't have the original function model, and so we really can't do a simple average using just a difference quotient. We're going to look at using the integral formula that we have available as well. So if you just type this in, this will be Math 9 in your calculator, and you'll type in the integral. Make sure you remember the 1 over 40, and you end up getting 5.916. And there's some other stuff. I'm just leaving the 3 decimal places there. And in this case, it is velocity, so the units would be miles per minute. And that does it for this particular FRQ. Okay, let's move on to the next FRQ. I'm on page 4 of the notes, and I'm going to look at the 2008 AB FRQ, which is number 2 that year out of the 6 FRQs. And in this one, I want to walk through the trapezoidal approximation. The last problem we did the midpoint Riemann sum. This is not called a Riemann sum because it's not a rectangular approximation tool. It's a trapezoidal sum. Quite common on the exam. You will most likely see this, but it's always hard to know what exactly they'll test on. So in this case, we have concert tickets. They went on sale at noon, which is t equal to 0, and were sold out within 9 hours. The number of people waiting in line to purchase tickets at time t is modeled by the twice differentiable function L in between 0 and 9. Values of L at various times of t are shown in the table above. Okay, so in part A, it says use the data in the table to estimate the rate at which the number of people waiting in line was changing at 5:30 p.m., which is time 5.5. This is one of those very traditional and common rates of change problems. Average rate of change as an approximate for instantaneous rate of change. Because it's time 5.5, we're obviously going to pick the most condensed time around 5.5, which would simply be from time 4 to time 7. And what we're doing is we're going to find the average rate of change over that time, which is just the difference quotient, and we'll use that as our approximation tool. So you could say that L prime of 5.5 is approximately L of 7 minus L of 4 divided by 7 minus 4. And that gives us 150 minus 126 given by the values of the table divided by 3. And you could do it in your head, or if you want, you can use a calculator because it's a calculator problem. And you simply get 8, and that is going to be people per hour. And that is all we need to do for part A. Pretty easy. Okay, let's move on to part B. So part B is the main concept here for this particular chapter, which again, or section I should say, which is going to be on approximations. And it says to use the trapezoidal sum with 3 subintervals to estimate the average number of people waiting in line during the first 4 hours that tickets are on sale. Notice how they don't say equal intervals. That's because if you were to take a look at just the first 4 hours, which is right here in the table, we are looking at 3 subintervals. And the only way you could possibly take this section and make 3 subintervals is to go from 0 to 1, and then 1 to 3, and then 3 to 4. So notice that they are not equal intervals, but the only way to possibly come up with 3 subintervals is the way we just talked about just now. Now with the trapezoid approximation, okay, and I'll sort of draw this out quickly because this one is very different from the other Riemann sums in a lot of ways, just because of the way that the trapezoid is set up and the way that you learned trapezoid areas and that kind of thing in the past. So let's say that you have some function that looks like this. And again, this is not for this problem, this is just in general here. So if you're going to go from the first data point to the second one, the trapezoid that is formed looks like this. Okay, and it actually follows the curve pretty well. However, when you think of a trapezoid traditionally, you think of something that probably looks a little bit like that, where you have, for example, base 1, and you have base 2, and then you have the height. And the area of this trapezoid is the sum of the bases divided by 2 multiplied by the height. Now, if you can kind of project this picture from the traditional way it's designed, probably the last time you saw it in either last year or in geometry, is that it really is on its side. So we have, this is the height here, this is maybe considered base 1 and base 2 like that. And then as you progress through this particular diagram, you would have other trapezoids that would align next to it. So it would look something like this. Some of them are going to be pointed in different directions based on the curve and all that kind of stuff. So that's what we're trying to calculate here. Now let's go back down to the problem, and we're going to look at the interval from 0 to 1. Now remember, from 0 to 1, that gives you the height. So we're calculating the sum of the bases divided by 2 times the height. So the bases are going to be 156 plus 120 divided by 2. And then the height is 0 to 1, which is, of course, 1. The next trapezoid, we are looking at bases of 176 plus 156 divided by 2. And this time, we're going to go from 1 to 3, so the height is actually 2. Then we have our last one, which is going to be 126 plus 176 divided by 2, and the distance is from 3 to 4, so the height of the trapezoid is 1. Now the problem also is asking for not just the total here, but it's looking for the average number of people waiting in line. And so the integral that we're calculating, I should have written this down first, is 1 over 4 minus 0 of the integral from 0 to 4 of L of t dt, and we are approximating it by this formula, which means that we actually have to multiply this by 1/4. And the reason is that we're doing the average value calculation. This was from the last FRQ we just talked about, and we're doing an average value calculator here, but we're approximating it with a trapezoid sum. So that's the idea behind this. If you use your calculator to type this in, you get 155.25, and what we are representing here is people. So that's an example of the trapezoidal sum, a very common concept that we're going to be tested on. Okay, for part C, it says, in between 0 and 9, what is the fewest number of times at which L prime of t must equal 0? And in the last FRQ that we looked at, we had a problem that was sort of similar to this in terms of its language. We're needing to utilize, in this case, the mean value theorem, but we're also having to utilize a little bit of the intermediate value theorem, and I'll show you why in a second. But the idea here is that based on the data in the table, there really is no way of coming up with an exact slope of 0 like there was in the last FRQ, which makes this more difficult. Okay, what I'm going to do is I'm going to pause and write out some of this, and then I'll talk through it. Okay, I'm sorry I had to move down. There's a lot here. This is not obviously the only way to explain this, but here's one example. And there's a lot here because of the fact that, as I mentioned just a minute ago, that the table, if you were to do the average rate of change, there is no L of t value that's the same as another L of t value, which means that we can't get a perfect average rate of change of 0. If we could, so for example, let's say that instead of 126, let's say that was 120, it would actually be a little bit easier for us potentially in the problem to figure out what's going on with the derivative slope being 0. Or if all of these were, let's say, increasing or something like that, it would be much easier. The fact that it kind of goes back and forth and increases and decreases, and we don't quite know how many times that occurs, this becomes a more difficult task. All right, so we know L of t is differentiable. It's stated in the problem. That means that the mean value theorem tells us that the derivative of L of t must be greater than 0 for some t in 1 to 3, as well as some t from 4 to 7. All we're stating here is that when you look at this little interval from 1 to 3 and from 4 to 7, we can see that L of t goes from, for example, 156 to 176, and then from 126 to 150. We know that because of the mean value theorem, the derivative must have a positive value at some point on each of those intervals because the average rate of change on each of the intervals is positive. So that's what the mean value theorem implies there. In a similar way, you can look at the table. In a similar way, the derivative would be negative for some value on 3 to 4 and from 7 to 8. So in a similar way, since the average rate of change is negative on those two intervals, the derivative must be less than 0 at some point on those intervals by the mean value theorem. With all of that being considered, since L of t is continuous, and the reason it's continuous is because it's differentiable, the intermediate value theorem says that L of t must be 0 for at least 3 values of t on 0 to 9. So think of it this way. You have a situation where your function is increasing at some point, then decreasing, then increasing, then decreasing. And if you were to picture that, you could then tell that there would be at least 3 values for which the slope would be 0. L prime of t would be 0. So that's what part C is. It's a very complex concept, and hopefully that makes a little bit of sense. You have to really think through the data in the table. All right, let's take a look at D. D is very quick. So D says that the rate at which tickets are sold is modeled by R of t, and based on the model, how many tickets are sold by 3 o'clock to the nearest whole number. Okay, so what that means is that we're going to integrate, we're going to accumulate all of these sales, and we get 972.784. This is math 9 in your calculator. And if we were to round to the nearest whole number, we would have approximately 973 tickets sold during that period of time. Okay, that does it for this particular FRQ. Okay, the last FRQ that I'm going to go through with you for this particular section is going to be from 2015, the AB calculus exam. This is number 3, which is non-calculator, and this is on page 6 of the notes. So we have this person jogging, and we have all of the velocity written in the table from 0 to 40, and the function v is differentiable. So those are sort of the highlights of the problem. So in part A, we're using the data to estimate the value of v prime of 16. Very similar to the first part of the last problem we did, where we're looking at estimating a rate of change. And so we're going to take all of the values that are the closest to 16 that we can, which is going to be between 12 and 20, and we're going to simply use the difference quotient to estimate excuse me, this particular derivative. So we have 240 minus 200, and we're going to divide by 20 minus 12, which is 5 meters per minute squared. So that's for part A. Pretty simple. Again, the key there is to make sure that you just take the data that is the closest to the value that you're trying to analyze, and we're estimating the derivative by the slope of the secant line. All right, let's take a look at part B. So we're using correct units. Explain the meaning of the definite integral in the context of the problem. So again, very similar to what we've been talking about here with these definite integrals and estimating these values. So I'm going to write out my response. I'll pause and do that, and then I'll talk through it. Okay, so this definite integral, similar to, we talked about that one in the previous problem where the velocity was always positive, and because it was always positive, the integral was representative of the total distance the plane flew. Well, in this problem, if you notice in the table, we don't have all positive values of velocity. So at 24, the velocity is negative. And so if there wasn't an absolute value, this would represent the displacement. However, because of the absolute value, this represents the total distance traveled over the time interval from 0 to 40. So remember, you want to talk about the context of the problem. So you don't want to just talk about distance period. You want to talk about how much Joanna is jogging over that period of time. But you also want to specify the period of time itself. You don't want to leave that off. So in this case, it's from 0 to 40 minutes. Okay, we're being asked then to calculate this using a right Riemann sum. So let me give you a quick overview of a right Riemann sum. If you have, this is just kind of a random graph. So if you have a set of data points, it looks like this, okay, and maybe a curve that represented this looked about like that. We're looking at the first point to the second point, and since it's a right Riemann sum, we're going to use the right side to determine the height of the rectangle. If this was a left Riemann sum, we would use the left side to determine the height of the rectangle. And that's how it would look. So we would have these rectangles. We want to take, obviously, the base, and then we want to calculate the base times the height. The height comes from the right side because it's a right Riemann sum. Okay, so let's go ahead and do that. In this case, we're estimating the distance traveled. And the first, I'll go up to the table here for a minute. The first one has a base of 12 because you're going from 0 to 12, so that's the base of the rectangle. And the height is from the right side. And remember, in this case, we're looking at 200 to be the height. So our first rectangle will be 12 multiplied by 200. If you look at the next interval, and I'll just do one more here, and then I'll put out the rest. But if you look at the next interval, you're looking at 12 to 20, and so the base is going to be 8 from 12 to 20. The height is based on the right side, which is 240. So the next rectangle is going to be 8 times 240, and then we have 4 times 220. Keep in mind that next one, the velocity needs to be positive because we're taking the absolute value. So I know it's negative in the table, but make sure that you make it positive because of the absolute value. And that's it. That's going to be our total. Now, without a calculator, you might want to just leave that. This does simplify to 7,600 meters, but again, without a calculator, you might just want to leave it kind of ugly like that. That's totally fine. Okay, let's take a look at part C. So part C says that Bob is riding his bicycle along the same path from 0 to 10. The velocity is modeled by b of t. Find Bob's acceleration at time 5. So we're asked to find the derivative of b, which is just the power rule. So we have 3t squared minus 12t. And we're going to calculate this derivative at 5. And if we just simply substitute this in, we have 75 minus 60, so we get 15. That's going to be meters per minute squared. And that's it for C. Okay, last part is part D. So part D says, based on the model from part C, find Bob's average velocity during the interval from 0 to 10. This question has shown up in each of these FRQs, so you can see that it's a relatively common theme. We're going to calculate 1 over 10, which is going to be the interval 0 to 10, so 1 over 10 minus 0 of the integral from 0 to 10 of b of t dt. That's what we're trying to calculate. We can do this because we have our equation. We're not approximating this. So the antiderivative would be 1/4 t to the 4th minus 2t cubed plus 300 t, and we're evaluating from 0 to 10. So we get, let's see, 1 over 10 times 10 to the 4th, so that's 10,000 divided by 4 minus 2 times 1,000, so 2,000 plus 300 times 10, so 3,000, very large numbers in this problem. You could certainly leave the answer here, but this does simplify to 350 meters per minute. And that's part D. So that does it for section 5.1. Thank you.